Okay. It's really corny, actually. Okay.
In 1869, Dmitri Mendeleev could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat. The elements we know about, they number 114. Some in quantities so small that they've never been seen. Most are common elements that are far and wide dispersed, but all of them together make up all the universe. Elements in group 1 are called the alkalis.
What is their property? Alkali metals. What is the very like a kind of unique characteristic about them? Yeah, give me more. They're highly reactive with halogens and with water. Okay, that's a fun fact. You should know that. With halogens and water. But they're highly reactive. But why are they highly reactive? Don't just memorize it. Go for it, Hayden. Okay, so what does that mean they do? They try to get more valence electrons? Or go for it? Right, they are so reactive, they are truly trying to get somebody to say, hey, get here, come play with me, let me give you this one electron. That's all they want to do is get rid of it so they can be like what? Noble gas, more to that electron configuration, right? It's not just to be like a noble gas, it's to be like their noble gas electron configuration because it's so stable, okay? So the reactivity is really related to their number of, say again? Valence electrons, okay? Keep that in mind.
Explode in water at a very tiny size. They love to lose electrons when they form a bond. Of these reactive atoms, I can say I'm rather fond. Group 2 elements are often called alkaline earth. Calcium's been building bones since well before your birth. They form nice +2 ions and are generally quite fun, though they're not quite as reactive as the metals in group 1. Since 1860,
they're less reactive because they have to do what with their electrons? They have to lose 2, so that's why it's just not as easy to lose 2 as it is to lose 1. Like, I don't know about you, but it's easy for me to lose 1 sock, but to lose both of them, that's got talent, you know. It takes some talent to lose both your socks.
69, every one of us could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythm.
So the periodic table, the whole reason it says periodic is because what is he saying that's kind of periodic? He's saying the properties repeat, right? So the properties repeat. So all of group 1, all of group 2, all of group 3, as you go across, you keep going back to group 1, group 2, keep going back to group 1 and group 2. So it's periodically repeating itself. That's what's called the periodic table. Does that make sense?
The pattern that can form a funky beat. Metals in groups 3 through 12 transition elements. Some of them are lightweight and others really dense. Things they have in common.
What is the most common characteristic you should know about transition metals? Yeah, Ty. They make color. They are the colorful ones, right? All of group 1 and group 2, we excited them in the flame, and those elements themselves did not make color. What in those elements made the colors happen in our flame test lab? There are electrons moving up and down. We can make anybody's electrons move up and down. That's why we had some iron and we had some manganese. We had all these other metals in it too, but specifically there were a lot of group 1 and group 2. So I don't want you to think that the metals made it happen. They're electrons. We use metal electrons because they're so loosey-goosey and they kind of are allowed to move up and down a lot better than some non-metals. So the things that form colorful solutions are transition metals. What are the inner transition metals? Are they D block or F block? Inner transition metals versus just transition metals. F block is they are actually within D block, right? So D block is transition metals, and then inner transition metals are the ones that fit inside of D block.
They form charges 2 or more, and some form colored compounds, which is something we adore. If you want an element, just tell me once again. If it's in group 17, you've got a halogen. Non-metals so corrosive, they're not found in their pure state. They can gain electrons like they're going out of date. Got one for you in group 18. It's known as noble gas. If you're looking for an element that just sits there on its... If you wonder why and haven't figured it out yet, their valence configuration is a big stable octet. So now it should be obvious that
Okay, so the point of this is like, which are the most reactive groups? Group 1 and 7. Why? It's all about their what? Valence electrons. Either you give one away or you take one. That's pretty easy. Group 2 is a little less reactive. Who's pretty much inert? Who's not reactive? 8, because they already have octet. So it's really, your reactivity relates to your, what again? Valence electrons. That's the main point I wanted to make there, and I thought the goofy video would help me too. Okay, so related to that, a lot of us think that hydrogen is actually, I know it's a part of the alkali metal group, but it's not an alkali metal, okay? Think of it as a separate entity. It's a gas. We all should know that. I think we talked about that. Why are these groups sometimes called families? Go for it, Hayden. They act the same, meaning they have the same properties. Okay, so if you're trying to match things like, oh, I'm really reactive with water, what group do I belong in? What group do I belong in? Huh? Group 1A, right? Group 1A or alkali metals. So your properties match the rest of your people in your family, right? And then the definition of AMU, that was on Reading Guide like 4, I think, 5 maybe. It's a random definition. You can look it up. Atomic mass units, okay? Oh, and then the last thing is the picture over here. This diagram, if I can move this out of the way, this diagram is the off-ball diagram, and what is it indicating again about like off-ball's rule? Off-ball, go for it, Hannah.
Electrons go the lowest energy level first.
And then all the way, right? And then they move on to the next energy level. So it's not going to be like you just put 1 in here and they're like, I think I'm going to go to 3 now, and then 4, and then drop back down to 2. You have to fill it up fully before you want to move on to the next sub-level. So 1 has 2, 2 has 2, 2p6, 3 has 2, 3p6. You don't just get to like half fill it and then move on. So that's very stable if you fill it that direction that way. All right, questions right now? DNA? We'll have some more time for questions. All right, so before you move, the carbon fiber research and climate change need to be both talked about in your presentations, right? So don't just focus on one side, focus on both of them. So I need to actually, I'm going to rotate around the whole time, like running around like a chicken with my head off. But I need everybody to be talking about what they learned and then presenting it into whatever, you know, your audience that was indicated on the project and the way that the role that you're taking on based off the presentation or product type that you have chosen, okay? So be serious, but I need to see where our groups are so I can match you up. So who's in Max's group? So actually get with your groups now and get anything that you need. Go to your groups now.
There's Courtney Joe's and Janie Knowles.
Okay, so get with your groups and I need to partner you up. You're gonna have to wait on partnering people. It's one of the class organizations. Okay, and freeze. All right, so I'm guessing group. Look at me. Group. Who's your whole group? You 3. Sorry, you 3. Okay, here's where I'm going to have you guys pair up, and you're only doing a 5-minute presentation. It's not going to take you long, okay? So you guys are going to present to them. You guys are going to present to them. Make eye contact. You guys are going to present to them. You guys are going to present to them. And then, I'll put you guys in. Okay, go near those people that I've partnered with, and I'll tell you when to start. You're starting in less than a minute. Get your lives organized. Carbon fiber, what's up? It's fine. You need to just do it. It's on my website. You just have to do it. Okay, guys, I'm gonna put you in your group 3. Can you guys get over there? They're smaller. Okay, you should be sitting near that group, and I want you to start in the next 30 seconds. You guys can rock, paper, scissors. Who goes first? Okay. Very technical way.
I've never wanted to. Yeah, you won, so you go win. I'm upside down. Can you guys see that? Just walks in like. I know how to do process where so not they're molecules so high. And then all the non-carbon we're not done. We haven't moved Oh yeah, do you know that carbon power doesn't rust like steel? Yes, you
lighter overall and
if you guys have about 30 seconds to finish your statement, okay, then we'll make some changes real fast. Okay. Yeah, it's not an extra 5. Yeah. Okay, give me your attention. 5, 4, 3, 2, 1. Sorry. Do you need more time to finish making your concluding arguments about if that person, if you requested funding and you got all your points made? Yeah? No? Yeah? Okay. Okay, as you're making your kind of final statements, the people that were listening to you, I'm sorry, I didn't tell you guys to grab paper. Get some paper, and I want you to write down the positives and negatives of what they were saying. Not just on carbon fiber research, because everyone's going to have kind of the same stuff there, but if their model of what they were doing was, possible, if it could be made into a reality, if they give them a ranking of like 1 to 5 on how well they presented their information, I'll write them on the board. But I want you to give them a couple of feedback points, and that's going to be given to me first, okay? And then I can make it anonymous with them. But you can just write down a couple of facts. So things I just said. 1 per person. So each of you can have your own opinion. So, paper. I'm sorry, I forgot to tell you guys that before.
I really don't want to know this. No, I can do that. Yeah, no.
Alright, but you guys might need to finish saying what you need to.
We finished that group project.
The 3 questions are on the board. And find out what you're focusing on. Take 1 or 2 minutes to make your response and then you're moving to the next one. Thank you.
you really know your racing dude.
I think it's just saying why, but that's okay. I didn't say
You have to give
What? Okay, next group is presenting in, I'll add a minute, and that's it. 6 minutes, okay?
got another minute. That's it.
Let's go. Atomic mass? I want to double check. Oh, I don't know. I thought it was like 12.05 divided by 100 times. No, 98.9 divided by 100 times 12.05.
All right. Next presentation should be in action. Sorry. Yeah.
It's kind of off topic, right? It's like, I forgot how to do it.
I'm gonna answer it after the carbon fibers because I need to rotate around. I'm sorry. Okay, go. Present.
How do you make it? First, you got to put it in the pot, you can spit it up, get it all mixed together, and then you stretch it out, strain it, wash it, clean it, get it all ready to be in a box size, which is white black. Then you heat it up, and then you. Okay, what is it made of? Only gas, and then carbon dioxide. When you take carbon dioxide, carbon, and you treat it to make it all rough, so that way you can put some glue on it, or mold it, whatever you want, characterized by long strips, that's carbon fiber. So all these tables and stuff.
So climate change, the main cause of climate change related to greenhouse effect. The greenhouse effect is when Earth becomes warmer when people transform radiating the Earth's surface to space. Atmospheric gases such as water vapor, nitrous oxide, methane, and carbon dioxide block the heat from leaving the Earth. Carbon dioxide is released into the atmosphere through human-related actions, such as deforestation, which reduces the amount of CO2 that is put into the atmosphere. Land use changes and burning fossil fuels. The amount of CO2 in the atmosphere has increased by 40% in industrial pollution. Methane is released through decomposition of waste in landfills, agriculture, digested and livestock. Because there are more of these gases in the atmosphere, more heat is being trapped, therefore increasing the Earth's temperature. This recent increase in the amount of heat being trapped due to the greenhouse effect is commonly known as global warming. Greenhouse gas emissions in the atmosphere will continue to increase unless we decrease the amount of emissions we're putting into the atmosphere. If action is not taken, these emissions are expected to increase Earth's average temperature and cause other climate changes which could greatly affect our well-being. The overall carbon footprint of carbon fiber composites over its lifetime is dramatically lower than that of steel. The reduction of carbon footprint helps save energy, fuel, and reducing the amount of CO2 being put into the atmosphere, therefore reducing the severity of the greenhouse effect.
Okay, so I got it. So we can use it in the wind industry, and it makes the blade super light So they can move super fast, which produces more energy. Also, it doesn't take as much fuel to swell them around and move to where they need to go because they're super light. You can use it in automotive industry because it makes the frames super light. You don't have to, it's lighted. You don't have to burn as much fuel. And it moves. Use it in the aircraft industry because again, it's lighter. Also, you can make the wings pretty much vertical almost and it makes more efficient to provide fuel. Good. So what we're trying to do is use the thing. Carbon fiber from you can make CO2 in the atmosphere and grind it out. It's been working pretty well, but it only works if you make a small amount. So what they want to do is grind it up really big. So that way you can take all the CO2 in the atmosphere that's causing the greenhouse effect and make it into carbon fiber, which can maybe stay emission resistant. And they do that by this is what okay, good. So you use solar power machine. Okay, current would take a cell and it'll suck in all CO2 and at the end of the current it makes carbon fiber. Something like that. Something like that. There's a statement and it's better. Oh wait, we did explain that. We're just kidding. And so I can do that. It's just better. And so it's more efficient and so for the environment. And the current method they're using on back, and this is renewable, and the one over there called Chem is not renewable. And so if these, this is how much CO2 is released into the atmosphere when you make carbon fiber airplanes. That's one time, but over the lifetime of the carbon, it saves 1,400 tons from going into the atmosphere. So the difference is like a lot. Saving cars, 20 tons, 50 tons. Carbon fiber. We should do this because it's such a hard to make and the leading factor in
Okay.
You really got
today. Today.
Miss Antelope. I'll be presenting to other groups.
I'm gonna have you guys just present right here for now because I need to watch the time for the rest of our day. Okay? I'll maybe have you guys present again at the end. Okay? Yeah. Same questions. Yes, ma'am.
Where are they going?
They have a third group. They have to get theirs done. Is that a problem? No. Okay. So finish your questions right now, and then come back to me, and I want to make sure we have time for review. And hopefully Skittleium lab. So let's get this party started. We have Skittleium that we didn't do yesterday because we started review yesterday. Yeah. After they've radioactively decayed to their safety. Yes.
Radioactively decay. I love having radioactive decay in my body.
Well, no, we're letting them decay so they're stable.
Were they not stable before?
No. How about Skittles?
Are those Skittles?
No, these are not Skittles.
Oh, I was like, what'd you do to them?
Yeah.
They're what?
Skittles? Yeah, it's just Skittles. They're from an Asian market. Don't tell my secret.
Alright, when you guys are done, come back up here, okay? Take 1 more minute. That's it. 1 more minute.
So
This was good. This was really good.
wait, is this the same thing as this?
Ty, bring me, yeah. Kendall, bring me a brochure. Actually, you know what? Let's do review first. Later, maybe. Post it later. Thanks, dear. Hey.
Remember that stuff That's what I said at the Chem, where I give AP we're allowed to make an excess of hydrogen.
Yeah.
You never said no, so.
But I never said yes. How much power is it?
But do you have the power to say yes?
That's like really
It's in this limbo.
It's like leaning toward yes, like the. Oh my gosh, no.
Okay, everybody in the room right now? Everybody in the room right now, just for a second, you're in the next minute. Please finish your responses, put them in the box, and then have your unit review on your desk where you sit after I change your seating curtain. Okay? So go back to the place where you're supposed to be sitting. If you need a laptop to pull up the unit review, grab a laptop and pull up the unit review. But I need to make sure we're on the right track before we go to skill meeting.
I said no. Why would you put it up? You broke it. What have you done? Oh, sorry. Oh my gosh. Why would you give this to Oh my goodness.
Until every year. Like you did it.
Hannah. I can't even get it. Oh my goodness.
Alright, guys in the back, please come up, put yourself in the box, and get started on your unit review. I feel like this is not structured. If we have to sit in our seats for the last hour and a half, then we will. Please do what I ask you to do. I want to see you guys. And that's something I have to Okay, everybody to your seat. What do you think you should do right now? For getting your unit review on your desk, it's already there. You need a laptop, grab a laptop. Otherwise, you should be working on your unit review right now. Anything? Yes. Please. Oh, shit, you guys just everybody. Put it in the box. Put it in the box. You need a laptop. You pull out that fine. Otherwise, and start working on it.
Matt.
Let me let's hear that. I'm gonna get some questions after.
You did this? You paid. Your stuff is right there. But you look back in time.
I'll answer questions in about 5 minutes, guys. Give me a second to go see everybody's degree. Alrighty,
that was open over.
But I need to pay them.
It doesn't Is that right there? Is that
I'll go over that in a second.
I think it's it. What's it? 20 seconds. Thank you. Bless you.
The person next to you might be a resource for the time being until I can get around to it.
This is on your desk.
Yeah.
Alright, if you had a question as you were working last night and you know you're like, I just skipped number 7 because I didn't know how to do it, then I'm going to go over it right now. But if you aren't there yet, then I would still listen because you're going to get there and then you might have the question, and I'd rather not have to do it again if I don't have to because I already answered it once. So, I'm here, 1 through 6. Any questions so far? Shout it out, yeah. Number 3. Element X has 2 isotopes, X100 and X104. The atomic mass is 101.03 AMU. Which isotope is more abundant? Who's got it? 100 or 104? Why 100? YX 100. You have a reason. I know you do. Hannah.
Because the average is closer to 100 than it is to 104.
Right, so the weighted average really does weight it towards the one that's more abundant. So 100 pulls that average down to closer to itself. So 101 is closer to 100 than to 104. If the average atomic mass was like 103, 103.5, it would be the 104 number because, or isotope, because it would be more abundant, pulling the average up higher, just based on the relative distance it is from the average. All right, another one, 1 through 5. Yeah.
Wait, going back to number 3, what if it was 102?
Then you wouldn't know. You'd say it's 50-50. If it was 102, it would actually be exactly 50-50.
Okay.
Yep, you could say neither. Trick question, Miss Inlow. Gotcha. Yeah, what's next? Yeah. 6. How many sublevels? Remember, sublevels are the letters, S, P, D, and F. Okay? They're the letters. How many sublevels are in the following principal energy levels? 8 equals 1. How many different sublevels have you ever written? One. It's called 1 as 1. Or 1 as 2. You know, the whole thing. So there's only 1 in first in the principal quantum number 1. In N equals 2, you go through S block and P block. So like 2S, 2, 2P, 6. So that's only 2 sublevels. N equals 3, what are all the associated ones? 3S, what's next? 3P, right, hun? So we're just simply talking about like what letters come with the third energy level. So there was such thing as 1S, there was such thing as 2S and 2P. There are such things as 3S, 3P, and 3D. So you'll see N equals 1, there's 1, N equals 2, there's 2, N equals 3, there's 3 different sub-levels. Let's go to N equals 6. 6S, 6P. Is there a 6D? I don't know, let's double check. Where would it be if it existed? On the 7th level, right? So 1, 2, 3, 4, 5, 6, 7. So that's 7S2. So what is this called? 6D. All right, so what is F block called? What's the number here? So that's N minus 2, right? So F block fits into right here, and that's 6S2. What's F? 4F14, and so what's the lower F? 5F. So is there really such thing as a 6F? Not the way we look at the periodic table. There's actually things that we think periodic table could be much larger, but that's like above our pay grade, okay? So we're going to stick with this. 6D. Okay, so there's only 3 there. So I think you get the gist. I think you can continue. All right, how about 6 through 10? Anything right now? Shout out. Yeah.
For number 7 for G, it says fifth energy.
How many orbitals are in the following sublevels? So the 5th energy level is made up of what, and what? 5S.
Oh, yeah.
What else? 5P. What else?
5D.
And 5F. How many orbitals are in the S block?
1.
1 orbital, but it holds 2 electrons, right? So 1 orbital, so keep that in your mind. How many in P? 3, so that's up to 4. How many in D? 5, so we're at 9. And then F? 7, so 16? Yep, 16 orbitals. So that's 16 orbitals just by adding up the dashes you would have drawn on like an orbital diagram. And with that, I could ask you how many electrons. Well, how many electrons if I got 16 orbitals? How many electrons fit per orbital? Right, this is an orbital, right? And you go 2. So we have 16 orbitals. How many electrons? 32 possible electrons. All right, keep going. Through 10? Yeah?
Which one did you just answer?
I just answered G. And that was 16 orbitals.
Okay.
Because we said the full 5th energy level is made up of 5S, 5P, 5D, and 5F. So it's made up of all those sublevels, and then you break down the sublevels to their individual orbitals. So 1 orbital, 3 orbitals, 5 orbitals, and 7 orbitals. We just added up the orbitals first. And then we said, oh, there's 2 electrons per orbital, so just double it. Okay? How about through 11? Should we keep going real fast? If you don't ask me. If you haven't gotten this far, you probably don't have questions, but you will. Okay, 14 through 20. 14 through 20, so for Hannah.
19.
19. Suppose your favorite AM radio station broadcasts at a frequency of 1600 kilohertz. What is the wavelength in meters? So, actually, I'm going to go over here and do this. So, if you set up a equation with hertz in it, that's actually the frequency. So, that's telling you V is 1600 kilohertz or per seconds. I'm gonna write this in a different way. How many little hertz is that? A kilohertz is the bigger unit, so how many little hertz fit in there? What's the equivalency between kilo and base? It's 1,000 difference, right? So if I have this many kilohertz, am I going to have more regular hertz or less? More. You're going to have 1,000 times more, right? Because there's 1,000 more hertz in a kilohertz. So I'm going to write that like that.
Emma,
Yes?
could I please have Matthew Brakeman for disposal?
Yes.
Thank you.
Okay. So this is how many hertz you have. I went ahead and converted that to hertz for you. All right, so here, if you want to get down to wavelength, what equation uses both frequency and wavelength in it? There's only one equation. C equals wavelength times frequency, right. So C is going to be your 3.00 times 10 to the 8th meters per second, and you're going to divide it by the frequency of 16.123 hertz, which is a per second unit. Again, it's just the weird hertz versus seconds. So when you divide that, you'll cancel out seconds, and meters will remain. And that is the question it's asking for wavelength. So I kind of set it up for you. I rearranged the variables right here and divided by that.
Good.
All right, another, yes.
So that's 1,600,000 seconds.
No, that's per second. Per second. Hertz is per second. It's weird. All right, so I'm just giving you basic setups for some of these, and you guys can go on. How about through 22? Yeah. 21C3. Okay, so let's just go through all of 21 if that's okay. So how many would be lustrous? So before I even start this problem, I go through and label these metals, nonmetals, metalloids, transition metals, stuff like that. So bromine, what is it? Metal, nonmetal, metalloid, or transition metal? Say again? Non-metal. Okay, so I just feel like a little NM up there. Non-metal. It's really tiny. S, sulfur. Non-metal. Vanadium. V. TM, transition metal. RB. Rubidium. Sing group 1. Group 1. Metals, okay? AG. Silver. Transition metal specifically, right? Okay. SV, antimony. It's on the metalloid line, so you might have it to figure out, but if you put metal or metalloid, I think you'll be fine. Oh no, how many metalloids? There we go. And then hydrogen is a non-metal and aluminum is a normal metal. Okay, so C, specifically color compounds come in what group? Transition metals. How many of these are transition metals? Vanadium and silver, right? Dose. How many would be solid at room temperature? What is that a characteristic of? Metals or metalloids, right? So any of the metals. So we've got aluminum, antimony, silver, rubidium, vanadium. So it's 5. So 5 would be solid at room temperature. How many would be ductile? Yeah.
Because you can have like a solid sulfur.
You can have solid sulfur, and that's a detail I leave out. But if you know that, I get it, and you can do that. Like bromine's actually a liquid at room temperature, and iodine is a solid at room temperature. So there's all the nonmetals. Some of them are funky and they have different states. But I'm just going to go blanket statement. Nonmetals are gases at room temperature, except for a couple that we will have some exceptions to. Sulfur is a nonmetal, but it is so attracted to other sulfur atoms it collects together to make S8. It's an allotrope of sulfur. Okay. S what? SV is antimony. It is definitely over here. It's a metalloid. Okay. Okay. Ductile though. What do we just say? Metal, rubidium, metal, transition metal, vanadium, silver, antimony, and aluminum. So that would be 5 as well. So you should see that anything that's a metal will also be ductile. Anything that's metal is probably lustrous. So I would say 5 as well. But sulfur, if you include sulfur in there, that would not be lustrous, right? You see how I'm trying to keep it as simple as possible. Okay, through the rest, if you've gotten this far, through 26. If you've not, it's totally fine. I'm just trying to answer people's questions before we move on to. Yay, nay? Yeah. 24. Explain why magnesium is smaller than atoms of sodium and calcium. So magnesium exists here on the periodic table. Sodium is right next to it. And calcium is one below it. Okay? So when I'm saying smaller, what am I really asking about? It deals with the proton number. Hold up, okay. But what am I actually, like, what's the word that we've actually used that represents its size? Atomic radius, right? So atomic radius is right hand, right? Okay, right hand down. To the left and down is bigger. And so magnesium is definitely, according to the trend, it is going to be the smallest of them all. So that just helps you kind of clarify, yep, that's definitely the smallest one. But if you're talking about anything going across a period, you used one factor that you explained. Anything down a group, you used a second factor you explain with. So magnesium versus sodium, who has more protons? Magnesium has more protons, therefore it has a more effective nucleus. So what's the term or factor we talked about for that? So magnesium has greater Zeth. Do you remember what Zeth means? It's more, what is the Z number again? Tell me one more time. What's the Z number versus A number? You're like, I remember. Yeah.
It's the atomic mass, right?
That's A number is the atomic mass. So Z number is the atomic number. And atomic number is just number of protons, right? So atomic number is just number of protons. So basically what this is saying is magnesium has more protons. Magnesium having more protons means it has an effective nucleus, and that effective nucleus is doing what to its valence electrons? Pull them closer. And if you pull them closer, you're smaller. Your atomic radius is smaller. So now that's only across a period. It has greater Z. If you're going down the group here, we can't really talk about protons and protons because there's one bigger thing that's way different. What have we just built? Yeah. But what is it based on? An extra what? Layer. What's that layer called? Orbital or energy level. I'm going to go with energy level. So there's calcium has an extra EL, energy level. And that's basically what the shielding effect is. So this has an extra energy level, therefore it's bigger than magnesium. So you can just stick it as simple as that, as an extra layer. All right, and that's the periodic transfer. Yeah.
We go over the chart.
I'll go somewhere the chart. Yep. So here's where I'm stopping. We have 50 minutes left in class because we get out at 12:40. So we have 45 minutes left in class. If you are done with your unit review, you can do the Skidlium lab. If you feel good about your unit review and like, I think I can finish this and make an A on the test tomorrow, you can do the Skidlium lab too. If you've not gotten even halfway through your unit review, please do not get up and do the Skidlium lab. You probably need to be sitting here working on this. So the Skidlium lab is, I'm going to put it on the back table. It's basically, you're doing radioactive decay, and once Skidlium, which is radioactive, is harmful, okay? Once it decays the blankium, the blank side of the skittle, right? The other side of the skittle, okay? Once it decays, it is safe to eat. Also, there are some good nuclear decay questions on here. The nuclear is on your test, mainly on multiple choice, so this is good practice for that. But I'm leaving this as an optional practice, because if you don't know this stuff, there's no way you want to do this right now. I'll make up a couple questions about the school. Okay. So basically, I'm going to leave this here, and at your leisure, get up, and I'm going to put a little thing of cups back there, and you guys just scoop a cup of Skidlium out. And then the instructions are very clear on here. But that's only, like I said, if you're mostly done with your review, or if you're like, I think I did this, I'm telling myself I'm going to finish it at home. But if you're not even halfway done, do not get up. So if that's you, go. If not, I'm going through the chart. This chart, right?
Yeah, I just need the first two columns.
Oh, beautiful. Okay.
I don't understand what A is.
The A to Z format looks like this right here. A to Z. A is the top number, which is atomic mass. Z is the bottom number, which is the atomic number. So this one's actually already written for you. Just put an arrow and say that. The mass format for this, which is the MN, so manganese, and then dash 62. Dash 62 means it's representing its mass. So if you forgot with the A to Z format and the mass format, they look different. They're the same isotope, they just look different the way they're written. sodium, A to Z format would be sodium 1 plus for its ion as it's indicated, but you have to, 1, look at the periodic table because you've got to get the atomic number, and 2, you also have to get a mass.
Wait, so if it's just a plus, that means it's 1?
Yeah, just a normal plus means it's assumed it's a 1.
Not like the
Electron number, right. Okay, so sodium here, atomic number of 11, mass number of 23 is its closest isotope, so you'd write it like that for its A to Z notation. And then for its mass notation, you just say sodium ion dash 23. Yeah.
What I did on my paper is I wrote 62, like the top or the proton, and then do I have to write the dash?
Are you talking about for A to Z notation or mass notation? Mass, you put the dash 62. Don't put it at the top or the bottom. It's like on the same line. It's just the way A to Z is like a subscript or superscript and subscript. This one's just flat.
Okay.
Yes.
Is that the same formula on your website? Because I didn't get the plus and minus.
Should be. Maybe it just didn't print. It's really tiny. Add it for yourself. Yep. I'm sticking with this right here. Yeah.
Can you do the fourth one?
2, 3, 4. This one. Okay. The only piece of information I give you is 37. Atomic number 39. Well, this is really the gold. This is the gem here. Okay. 39 is potassium. No, I lied. Yttrium. Thank you. All right. So there we go. Yttrium. I believe you and stuff. Yeah, 39. Okay. And so that atomic mass number here allows us to write both these things together as yttrium 89, 39. Sorry, 39. That's really hard to see. So there's the A to Z notation. The mass notation is yttrium 89 because that's its mass. And then at this point we need to consider this other piece of information because we've used this and we've used this. 37 is going to be important because atomic number 39 means it has how many protons? 39. Well, it's telling me I only got 37 electrons, so you know it's not neutral. So what is the charge of yttrium? 2 plus because it actually has 2 less electrons, 2 less negatives. So this would be a 2 plus, 2 plus, 2 plus. I'm sorry. 2 plus. There we go, all the way across the board. So that knowledge helps you know that you have a charged ion that's an ion. And then number of protons, you're like, oh, can't change protons because that is totally against law unless you're a nuclear chemist. And that 39 transfers that way. And the number of neutrons, you base off the mass. And what do? Subtract the protons, right? So mass subtract protons gives you neutrons. So 89 minus 39 is 50. Yep. Yeah.
What's the number of neutrons for the second one?
This one, sodium one, it's got 11 protons. It's apparently got 12 neutrons. Is that what you just asked me?
Oh wait,
It was given to you in that box.
I just got confused because the plus is there's 10 electrons.
Yeah. So 11 protons is a standard, and then with a 1 plus charge means instead of having 11 electrons, you've only got 10. 10 electrons. And its mass number is just protons plus neutrons, so 11 plus 12 is 23. Okay. Any more questions, or you guys keep working and I'll just run around. Okay? Yeah.
So can you explain how you got
We went over like the orbital information a while ago, but basically the s orbital is a sphere. Can you draw a sphere any other way? Right, you can't, right? But the p orbital is a dumbbell. You can draw it in the y-axis, so that's one orbital. The x-axis, which is the second orbital, and the z-axis, which is the third orbital. So that's why s's only have one orbital, p's have three orbitals. D's are like that double dumbbell.
Yeah.
And then there's 5 different orientations. There's 5 different orbitals. And the F is like a fly. And I don't even know crazy different orientations they take on, but there's like their second. So that's why we said the fifth energy level can do 5s. It can do 5p. Well, so far that's 1, 2, 3, 4 orbitals. It can do 5d, which is another 5 orbitals. That's 9 so far, and then 5s is made of a total of 7. So that's what it's doing. It's just about that. Be right back.
So, since it's unknown, that we've got like first 3 with orbitals. What's up with
That's what, Hannah, that is this. This is all Fall's diagram, and it's like we were talking, 1s2, 2s2, 2v6, 3s2, 3v6, 4s2, and then look, the energy, this is energy on this side. Not energy level, just amount of energy. And so you can see that after 4s2, it's 3d, and then 4p again. So we have to know his diagram, but we don't have to memorize the diagram. We can follow the periodic table. So that, yeah, energy versus energy level is hard to distinguish, but I think you got it. Is that your only question? Yeah, I'm making noise, but don't worry. I'm going to post it. That was my note to myself to post it, but you can see it there as well. Okay. I think I know. You're trying to figure out how you become a non. Give me more.
Okay. If it was like RV -2, like, how would you do it? Like, I don't know. How would you write it? Yeah. How would you write it? It's like, yeah.
The first thing you do rubidium, because rubidium is very reactive. It has one beta station. It is very likely to lose oxygen. Very commonly uses rubidium plus an ion phase. And that's when you lose an electron, that's not very romantic, it's free to leave. And so when you lose one of those 37 electrons, you still have 37 protons. But 37 protons, 36 electrons. You have overall 1.1 positive charges. So therefore we say it's really good. Oh, okay. So you just got one more proton. Okay. But like oxygen here, oxygen, so these ion groups we make, I don't make them up. I try to figure out what they usually are. So oxygen itself, you told me, something else like
Oh, yeah.
So 128, 38, 38. So it's 6 groups of 6 basic electrons. Okay, it all has a turtle. It's turtle. Right, so how many electrons is it? Lower 2 versus that. Yeah, whatever. So it gains 2 electrons. Going back to your normal one. 6 and 6.
If it was O plus 2, it would be. So you're missing.
Who had a question up here? Kendall, I'm right there. Let me get some vocabulary taken care of because I've had a lot of questions about this.
I want all the sublevels.
Okay. So it's weird. The vocabulary really means something. This is the P sublevel with 3 p orbitals. 1, 2, 3. But the p sublevel is just generically p. Does that make sense? There are 3 orbitals in 3 different orientations.
But there's the orientations and the orbitals.
Yes, the orientations are the orbitals. But if you just said p sublevel, you're not identifying any of them. You're just saying all of the orbitals are p. All 3 of them. All of them. So if the question was, what was it, 5th energy level? Or the 5D? What was it?
It was just the 5th energy level.
Well, you were asking about 5S, right?
Yeah.
So the 5S is just simply the fifth energy level. So it's big, but it's a big S orbital. That's an S orbital. It also happens to be the S sublevel. The sublevel is the orbital because it's like one and the same. There's only one. So that just happens to be bigger. So it's because it's got like, energy levels underneath it. But if I compare that to like the 1S, that would be the orbital. It's the same shape, it's the same orientation, it's the same whatever. It's just this one's bigger. That's the only reason it's any different. It's just one orbital. And then the F's are even weird. They're very weird. But like you said, the 5th energy level, that consists of everything. That consists of 5S, which is one orbital, 5P, which is 1, 2, 3 orbitals, 5D, and 5S. And you add all those orbitals up, and that's 16. Yeah? Okay. Tideja, I'm coming to you next.
So we're going to be doing this. Yeah, but
Now you're
I was halfway here. You go down.
20? Was it 6 what? You convert that using dimensional analysis to meters. And we all talked about it. We were like, nano-9, 10 to the 9th is nanometers. So there are 10 to the 9th nanometers in 1 meter. So that divided by that gives me 6.70 times 10 to the negative 7th meters. And all I did was switch the decimal back 9 spaces. Okay? So that is wavelength. So that's where you plug in for wavelength, no C, so then take C divided by wavelength to get B. And just as a side note, the color perhaps you use the color is you reading the wavelength and how many seats?
says how many orbitals are in
The 1s sublevel is also the 1s orbital because it's just one in the state. Caroline, come up here with that question.
But when it changes letters, is that an orbital?
No. 4D is just the D sublevel. That's at the fourth energy level. That's like really high energy level. But it's still just the D sublevel. So how many orbitals are in the D sublevel? 5. The letters are going to change, the numbers are going to change. But look at the letters.
So does the number
Not for that.
If it says 7+4, how do you minus those two?
We were just talking about the whole valence selection. How you lose your valence selection, so what you know that is the valence electrons exist in a very outside energy level. So when you're looking, you have 2 energy level, 3 energy level, 4 energy level, 5 energy level, a 4 energy level, right? So the 5 energy levels are still the valence electron shell, where the valence energy levels are the very outside energy level. So when you lose 4 electrons, when you lose 4 electrons, because you have an overall 4 plus charge, that has to come from the energy level. So you do those. That was supposed to be 2. It's 10. It's right there. You see 10? So it's only 2 entities. You added 4. I see what you did. You added 4 electrons. But if that were 5 and 2, you totally get rid of the 2 electrons, then you get rid of the electrons there. And it would leave you like that. And that would be
You just leave. So if it's the greatest energy level, you only minus from the 5s.
and it actually should have, like, if you had seen it, you would have like, oh, 2 by 2 there, 2 there. Oh, you're higher fifth energy level. Because that's always what you do. You either gain enough to fill your outer shell, or you lose your entire shell. You don't go down.
So for this one, it's just that, and then 3d6 because you're adding.
Or you have electrons. Because they're negatively charged, you're adding 3 negatives.
So you're adding 3 electrons.
Yeah.
Okay. Thanks.
Allie, do you have another question?
Yeah.
I didn't know
It's like funny.
I didn't know what you were saying.
Okay. That one's the one that we got from the
If you have a question, I hope you're moving on and not waiting on me, because that would be a horrible use of your time.
So what? Wait, hold on. Okay, so let's get back on the line and then you look at any wait, what is it? Is this the one? Anyone? Yes, because oh, it is like the bigger number. So it's this one. And then you look at the how do you say that?
This is my
There's no one key.
These are all the animals.
Yeah.
That's why.
What's the aspect?
So, what we ask is, the only,
third one.
Actually, no.
No, that
Third
one
one.
has D too, right?
Because it's three is S, because when you go on to the fourth level, we're subtracting
I mean, my mom's in Boston.
That's adding seven, get down.
I know the minus one, but I don't know the so it was where do you take away?
Sorry, practice.
What you're trying to find. So because barium has charge, so you say it's still you're not changing the proton, so it's still one barium.
But do you just like do it for two back?
Yeah, but you leave it with as but it's still
Okay, that makes sense.
so you stop at 5. Yeah.
So when you have a number,
Did I write 23? Then that's my bad. Number. I am doing number 14 on the board, okay? If you need help on number 14, watch now. Highly come for me so other people can see. 14 is an average isotope problem, and you will have one like this on your test. I think it's got 4 isotopes, though, not 2. So, 2 of the most abundant isotopes are carbon are carbon 12, block. Carbon 13, block. Their relative abundances are block and block. Calculate the average atomic mass. So, I'm going to write it up here. You take the mass, 12.05 AMU, multiply it by its average atomic, its a relative abundance as a decimal form, meaning divide by 2. So 98.9 goes to 0.989. Then you take the second isotope of carbon 13, aka 13.12 AMU, and you multiply it by its average, its relative abundance as a decimal form. So 1.1 as a decimal is, so 1, 2, so 0.0110. You take that and that, so the product of this, I'm not sure what it is, and then what do you do? Add them. That's it. No dividing by 2, no ponies and puppies, like that's it. Just take it, multiply, and then add the sums of those, and that's the only thing you gotta do. And if you want to tell me the actual answer here and here, I'll write it up there. But you're going to take the two oblongs and add them together. Okay? 1 second. Things I need to say before you go. Are you dating?
No,
Yeah, let me know. Okay. So, I have progress reports for you. I can give them to you today, but I can also give them to you tomorrow. Progress reports are not due. Progress reports are not expected to be updated until tomorrow, but I printed them because I've seen people with like zeros on homework that they literally just haven't turned in. You probably have it, or even if it's halfway done, turn it in. That's still a 5 out of 10 versus a 0 out of 10. So I want to pass those out. I will be here after school for tutoring, no, Teal doesn't help you tomorrow, does it? Sad day. No, I'm saying you won't have me before Teal. You'll have me before Teal. Yeah. Otherwise, I will update the website to include the PC, the portfolio check, which will include Unit 2 notes, nuclear reading guide, because I didn't take it up, so I want you to study it. I hope you guys are listening too, and not just taking Skittles out of bags. Adam's bingo, that bingo thing we did yesterday, the spectroscopy lab unfinished is totally fine. I want to see what you got done on it. And the last thing I added, I didn't say yesterday, was the history table where you went around and shared with your people. Your scientists, and I'm taking up those because I want you to right now really get those together because that's probably the best thing for studying. Plus unit review that I didn't write up there. How did I not write the unit review? But there you go. So unit review, notes, reading guide, Adam's bingo because that's basically unit review itself. Spectroscopy lab because everybody, I'm just going to say it, we all suck at the light stuff. We've embraced it, but we're not going to embrace it for long. We're going to write our units on our test tomorrow. And then the history table. Not all of us. Some of us are superstars. Yeah.
So you want to go back? Just your unit.
So that.
I have a 0 for reading that before, but I was asked if it was new. I think I gave it to you yesterday or Friday. There was no passing. Yeah.
Laptops up. I'm just going to say your name if you want your box right now. So come get it now. Suzanne. Wynn. Zachary. Khadijah. Sally. Hayden.
So we need to come
Caroline.
to the spectroscopy and
Anything from the portfolio?
it'll be in the check.
Jalen, Samara, Sarah, Kai, Kendall. What do you mean? Jalen? Get out of the way. It's right here. Yeah, Danielle's not here. Jack, Lizzie. Yeah, not yours. Oh, boy, hold on. Audrey, Emma, Alyssa, Annabella, go! Jacob, Kathleen. Max, you want to ask? Neely, Natalie, Max, Rebecca, Kyla, Talia.
Sorry.
Jake. Okay. Oh my God. Hold on. Emma, here. Emma. Oh, Emma, sorry, I got you the wrong one. That's Rebecca, yeah. Okay, can you see this?
Are you going to put the SMB to the clear line?
Right. I didn't turn these in for a carbon folder.
I'll take over from tomorrow.
I didn't finish the Skittles lab. I did all the tests and stuff. Do you want me to go home and get graph? Questions like
Just
that?
the graph, no questions for me. I think that you guys should have good experience.
So we'll just turn that in tomorrow.
Yeah, and I need to get my fourth period ready, so questions from third period have to be asked now.
The lab that I wasn't here for, don't you?
Bye, YouTube.
Or after school.
Which lab?
With the changing lights.
Howdy.
Hey, you're gonna, the spectroscopy lab?
I think so.
Okay, you'll have to do it during teal. I don't know if I can get it, if I can get it cut tomorrow. Or no, there's an online one. I'll show you where it is. Email me. Okay. And I realized my email didn't send it to my draft folder, so I'm really sorry about that. Okay, talk to you. I need to get ready for practice.
The scientist thing I didn't turn in. Do you want me to turn it tomorrow?
You need that ASAP. That's your project was due Monday. Okay. Get it to me. Go.
This is for all the things I broke.
Oh my god!
Sometime about 4 p.m. about 30.
That was bad.
No, but I didn't.